All right, tonight we're going to talk about carboxylic acid derivatives and the concept of acyl transfer. Now, there's going to be a ton of functional groups we talk about tonight. Lots of different ones, but they're all going to be the same. All the reactions are going to be the same once you understand the notion of the acyl transfer reaction. Acyl transfer reaction is an addition-elimination. So you're going to add to a carbonyl and something's going to leave. You're going to transfer an acyl group. It's really a very basic, very fundamental reaction. And once you understand that, once you grab the concept, all of the reactions we talk about will be the same. When we talk about acyl compounds, we already did carboxylic acids. Today we'll do acyl halides, anhydrides, amides, esters, and nitriles. All of these reactions are essentially going to be the same. Addition, elimination. These involve what's known as a tetrahedral intermediate. When I speak of acyl transfer, what I'm talking about is a carbonyl, some sort of carbon stuff on this side, and an X group. Could be anything. Okay, it's an X group. And we have a nucleophile that we'll call Y. And what's going to happen is this is going to attack the carbonyl, and it's going to form a tetrahedral intermediate. Now, this intermediate can do two things. The electrons on the oxygen can come back in to reform the carbonyl, and Y could leave, and it would go back. Or electrons could come in, and X could leave. And when it does that, what you have done is transferred the acyl group here from X to Y. Acyl transfer. All the same basic mechanism: addition, elimination. Any questions? Very simple, basic concept. Now we have lots of compounds to talk about. And the first thing we always have to do so that we can all speak the same language is to talk a little bit about their nomenclature. Now once again, on this next exam, nomenclature is going to be minor because we have so many reactions that are so much fun. But we have to go through it anyway. We did carboxylic acids. We said that a carboxylic acid was an oic acid with the chain attached in front. And if this was attached to a ring or was a substituent on somebody else's chain, we would just add carboxylic acid to the name. Well, if we have a halogen, we're going to do the same thing. We're going to call it an oil halide or a carbonyl halide. This is an acid anhydride. This is an amide. If it's a substituent, we call it a carboxamide. An ester is an oate or a carboxylate as a substituent, a nitrile or an onitrile if it's a substituent. So let's look at these one by one. The rules are all going to be basically the same. The acyl derivative, if there's nothing else that's bigger on it, is going to be the parent. So you want it to be the parent chain. You want to give it the lowest number. You'll list our substituents, whatever. So for an acid halide, we're going to drop the E from the alkane and add OYL. If it's a substituent, we'll call it a carbonyl. So here's a couple examples. Here we have a 2-carbon parent, so that's an F. It's an acid chloride, so we will call it an F-anoyl, and because it's an alkane, oyl because it's a acid halide, chloride, 2 separate words, F-anoyl chloride. This is also called acetyl chloride. Nobody would know what you were talking about if you called it that. Here we have a benzene ring with an acid halide hanging off. There are really 2 ways you can name this. Remember, the benzene ring is accepted by IUPAC as a good thing. It can be apparent. So we could call this a benzoyl chloride, and we'll see examples of that. If we wanted to name this as a substituent, we would say this was a benzene carbonyl chloride. Benzene carbonyl chloride as a substituent, or simply recognizing it as a derivative of benzoic acid, it's benzoyl chloride. Any questions? Let's just run through a set and name them quickly. Step 1, you want to look where your acid halide is. Remember, it must be on the parent chain. You want to give it the lowest number possible. For this guy, we have our acid halide, and we have 1, 2, 3, 4, 5 carbons. So it's going to be a pentanoyl. We have an ethyl group in carbon 2. So it's going to be a 2-ethyl pentanoyl chloride. Isn't it amazing how I can do that? Here we have another one. We're going to make our chain go this way so we have the most substituents. It's going to be a 1, 2, 3, 4 carbon chain, so it's going to be a butanoyl bromide. On our butanoyl bromide, we're going to have a 2-ethyl and a 3-bromo substituent, and we would put it together like this. 3-bromo, 2-ethyl butanoyl bromide. Now over here, we have an acid halide attached to a cyclohexene ring. Now again, when we talked about carboxylic acids, we pointed this out. We really want to make carbon number 1 one of these guys so that we can number through the double bond. But the acyl group takes priority. So it must be carbon number 1. That means that we have a 2-cyclohexene. This is going to be a substituent on the cyclohexene. So it's going to be a 2-cyclohexene carbonyl chloride. Now, there are lots of ways to name this one. Once again, we could make benzene the parent and this be a carbonyl fluoride substituent, or we could simply recognize this as a derivative of benzoic acid. If it's a derivative of benzoic acid, this will be carbon number 1. And we would have a benzoyl fluoride with a methyl group in carbon 2 and a bromine in carbon 5. 5-bromo-2-methyl benzoyl fluoride. Any questions? All right, same thing again here. We're going to do anhydrides. Anhydrides are a little bit different. Anhydrides, we take 2 carboxylic acids, split out water, and stick them together. There are 2 possibilities. The 2 ends can be the same, or they can be different. If they're the same, we use the modifier-bis and just say it's 2 of them. Bis means 2 of them. We're going to use oic anhydride to say it's a carboxylic acid. It's an anhydride. Again, if they're the same, it's a bis. Now this is acetic anhydride. We've all used this, we've all seen it, we all know it. What it is, really though, is an anhydride of ethanoic acid. So 2 carbon units linked by the anhydride linkage. And they're both the same, so this is a bis ethanoic anhydride. Again, acetic anhydride is what everybody calls it. Now here they're not the same, so we have to name them differently. This is going to be ethanoic. This is propanoic. So we'll arrange it alphabetically. Ethanoic, propanoic, anhydride. Any questions? So let's go ahead and go through our problem set. And let's name these guys. First thing you have to do is figure out, are the chains symmetrical? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes, it is. So it's a bis. 5 will be pentanoic, and it's an anhydride. So we would simply call it bis, propanoic, anhydride. Now this is not symmetrical. We have an ethanoic on this side and a 1, 2, 3, 4 that's butanoic on that side. So we'll simply string them together. Butanoic, ethanoic, anhydride. Now the next one down here is a dimer of benzene carboxylic acid, isn't it? And we could call it benzene something or other, anhydride. But we're not, because we all recognize that this is a derivative of benzoic acid, and our UPAC likes benzoic acid. Very old name. Therefore, we could just call this bis benzoic anhydride. Now this last one really challenges all the rules. In order to name this in an acceptable way, you could do it the really hard way, which we won't, or you could do it the easy way. The easy way is to say, well, what would this be if this was an acid, a diacid? 1,2-benzene dicarboxylic acid, anhydride, has the name of phthalic acid. So therefore, this is phthalic anhydride. Again, it's a combination of old nomenclature, but it is totally accepted by IUPAC. Amides. Amide is a very important functional group, both in organic chemistry and in biochemistry. Remember, in biochemistry, the amide linkage is what biologists call a peptide bond. That's what holds together proteins, hydrogen bonds, and all sorts of stuff. We'll talk about that in just a little bit. We're going to stick on the word amide at the end. Remember, it's a nitrogen, so we can have substituents. We use an uppercase N to indicate that. The only real difficulty in writing the name here is learning how to write an italic N. Here we have a 2-carbon amide, so it's going to be an F. It is an amide, so we're going to call this simply ethamide. This is also acetamide, a derivative of acetic acid, and that's what everybody would know it as. Now we've taken acetamide and we've stuck a methyl group here on the nitrogen. This is going to be, according to this, in methyl acetamide or in methyl ethanamide. Now, one thing we'll point out later, the nitrogen actually interacts with the carbonyl here. Now, this is an sp² nitrogen, which means that the orbitals, the p orbitals here, are coming out and into the board. So they overlap the carbonyl. And just like a double bond, that means we have hindered rotation around this thing. So we can have actually 2 isomers, one with the methyl group up and one with it down. Rotation is fairly slow at room temperature. Let's do some quick ones. Again, 1, 2, 3, 4, 5, so it's a pentamide with an ethyl group in carbon 2. Over here, we're going to go this way again. Let that be carbon 1. Going to be a 1, 2, 3, 4, so it's a butanamide with an ethyl group in 2, a bromine in carbon 3. Now our amide is a substituent on the cyclohexene ring. Again, this will be carbon 1. And we would call this 2-cyclohexene carboxamide. Remember, carboxamide if it's a substituent. And finally, over here, this is going to be a derivative of benzoic acid. We're going to call it a benzamide. It's a derivative of benzoic acid. In fact, the lab we do next week is called benzamide. We're going to make it. So by a very simple reaction. We'll talk about that. But, so this is a benzoic acid parent, and that will be carbon 1. We're going to have a 2-methyl-5-bromo N-methyl benzamide. But you have to name everything. N-methyl-5-bromo 2-methyl benzamide. Now our last 2 lab periods we have made carboxylate esters. Carboxylate esters, well, you drop the E and you make it an oate. Not oic acid, oate. You're going to stick the alcohol in front. If it's a substituent, we'll call it a carboxylate. This is ethyl acetate. We made that. The alcohol always comes first in the name. This is derived from ethyl alcohol. This is acetic acid, so it's acetate. More properly, it's a 2-carbon carboxylic acid, so it's ethanoate. So it will be ethyl ethanoate. We have a ring which makes this guy a substituent, right? So we're going to call it a carboxylate. The alcohol comes first. This is a methyl cyclopentane carboxylate. Any questions? And of course, we're going to do 4 examples. You've probably figured out the pattern. Here's our 1, 2, 3, 4, 5 carbon parent. Our alcohol is methanol. So it's going to be a methyl pentanoate with an ethyl group here in carbon 2. Aim the alcohol first, and then the acid with an oate on the end. Here our alcohol is ethanol, so ethyl will be our first word. It's going to be a 1, 2, 3, 4, so it's a butanoate, ethyl butanoate with a 3-bromo and a 2-ethyl. Ethyl, 3-bromo, 2-ethyl, butanoate. All right, we're getting crazy here. The alcohol is cyclopentanol. So cyclopentyl has to come first. Okay? Carbon 1 will be the carbon on the ring. And as we've seen before, this is a 2-cyclohexene. So we're going to have cyclopentyl, 2-cyclohexene, ethanoate. No, carboxylate, sorry. And our last one, go ahead and quickly jot down the name as a derivative of benzoic acid. Remember in your name, the alcohol will come first. So it will be a methyl. On our benzoic acid, we have a 2-methyl 5-bromo benzoate. Methyl for the alcohol, 5-bromo 2-methyl, benzoate for the acid. All right, let's do nitriles. We actually talked about nitriles back in chapter 20, but we'll just review it here. If a nitrile is a substituent, it's an onitrile. Otherwise, we drop the E and simply add nitrile. It could be a carbonitrile as well, if it's attached to a ring. So we either have nitrile, carbonitrile, or onitrile. Those are our 3 examples. Remember to count the nitrile carbon as one of them. So that's 1, 2, 3, 4, 5. It's a pentan nitrile with an ethyl group in carbon 2. Over here, this is carbon 1, 2, 3, 4. So it's going to be a butan nitrile with a 3-bromo 2-ethyl. Once again, this will be carbon 1. So this is going to be our parent. It's going to be a 2-cyclohexyl, 2-cyclohexene carbonitrile. And an example where we would use onitrile. This is a derivative of benzoic acid, believe it or not. The nitrile is the same oxidation state as a carboxylic acid. So that's why the 2 are linked together. So this is a benzonitrile. Going to be a 2-methyl 5-bromo benzonitrile. Now again, there's lots of functional groups here we talked about. Carboxylic acid from chapter 20 is an oic acid or carboxylic acid. Oyl halide or carbonyl halide. This is just an anhydride. This is a amide or a carboxamide. Oate or a carboxylate. Nitrile or an onitrile. Nomenclature, again, is going to be a small part of the exam. But, you know, it's important that you at least get a feel for these things and realize it's really pretty simple to name. You just have to decide if it's the main chain or a substituent, and then, do it. Any questions? Well, acyl compounds, we've talked about them in terms of spectroscopy. For the C13 NMR, when we look at carbonyls, the 2 carbonyl carbons that stand out are simply ketones and aldehydes. They'll be 200 and above. Acyl carbons, so this whole group we just talked about, are much less. They're about 171. So they're not quite as deshielded as these guys are, mostly due to interaction of the things that are attached to them. So for an ester, we have 171. There's an acid, 176, 171 for an amide. Now this is really pretty, well, this is an unsaturated ketone, so it's cheating. And again, it's up all the way close to 200. But for most of them, most acyl compounds are going to simply be right around in the mid-170s. Ketones and aldehydes, 200 and above. Makes it simple. The infrared, remember we looked at the carbonyl stretching lots of times. The actual wavelength of the carbonyl stretching is interesting because it reflects the reactivity of the carbonyl. The more double bond character you have, the higher the stretching frequency will be. Down here we have an amide. The amide is the least reactive of all of the acyl compounds. It has the lowest stretching frequency. Up here, acid halides at about 1810 are the most reactive acyl compounds, and they have the highest. So simply by looking at the carbonyl stretch, you can get an idea of how reactive the particular carbonyl is. In the lab, we just made isopentyl acetate. The carbonyl stretching frequency was 1745. Again, typical for an ester. More reactive than a simple ketone or aldehyde, much more reactive than an amide, but not as reactive as these guys. Now I talked about the addition-elimination mechanism. We're going to go through this a lot because it's actually the heart of acyl transfer chemistry. Here we have a carboxylate ester. This would be methyl acetate or methyl ethanoate. We can react this with Grignard. This is a reaction that we talked about a long time ago. The Grignard carbanion will attack the carbonyl carbon, and we will get a tetrahedral intermediate. Now, you know, this is written as an equilibrium. The equilibrium simply means that the electrons can move back in, and the methyl group could go away. That's really not going to happen, though. What's going to happen instead is these are going to go in, and our leaving group here is going to be the methoxy group. We'll talk about why in just a minute. And we will wind up with the ketone and methoxide. Now we know that when we have an ester and a Grignard, we add twice. So this is going to add again to make our tertiary alcohol. The thing I want to point out is the leaving group. In this case, it's going to be methoxy and not the methyl that you just added. If we have an amine add to a carbonyl, we form this intermediate. It's a zwitterion, plus minus. This is a very unstable intermediate. In the bat of an eyelash, or maybe 10 to the minus 8 seconds, it can go back to starting material. If, however, methoxide were to leave and we lose a proton, this would go to form amide and alcohol. The thing that we want to try to understand is what determines what group is going to leave to give us product. So let's look at a tetrahedral intermediate here and try to figure this out. If we had this tetrahedral intermediate, it could break down two ways. The electrons could move back in. Methyl group's not going to go anywhere. It's a carbanion if it left. That's not going to happen. But we could lose the methoxy group, and we could form the phenyl ester. That's one possibility, right? So methoxide leaves as methoxide, and we have a carbonyl here and a ester of phenol. One possibility. The other possibility is we do it this way. Electrons move in to make our double bond, and phenolate anion is our leaving group. And we have just made methyl acetate. Now, which one's going to prevail here? Which one is going to predominate? How do you know? It's actually very simple. If you note, in both of these, we're forming an anion from our leaving group, isn't it? Nature likes stable things. The most stable anion is going to leave. What is the most stable anion? Well, it's the strongest acid, isn't it? So if we simply look at the two acid dissociation equilibrium, one leaving group here is methyl, methoxide, that's methanol. This is phenoxide or phenol. What are their acid dissociation constants? 16 and 9.5. Whichever leaving group is the strongest acid is going to be preferred. So phenol is going to leave preferably by a factor of 10 to the 7th, because phenol is a stronger acid than methanol. So if we had this intermediate somehow, the product would always go this way, and this would be the products we observed. Yeah?
We have to figure out pKa to figure that out every time.
Don't you know that? Of course you know that. All right, here's another one. If I told you, because you didn't know, that our pKa's here, or -5 and 9.4, draw the products that we would get by the breakdown of this tetrahedral intermediate. Chloride is one possibility. Conjugate acid is hydrogen chloride, HCl. pKa is -5. Phenol is the other possibility, pKa of 9.4. Which one is the strongest acid? Well, HCl, of course, is the strongest acid. So this tetrahedral intermediate will partition. Partition is a word we use. This way, chloride will leave, and we will get phenyl acetate and chloride anion. look at what's around your tetrahedral intermediate. The strongest acid is your best leaving group. All the reactions that we're going to look at are going to follow this exact same mechanism. We're going to add, excuse me, form a tetrahedral intermediate, and the strongest acid will leave. All right, here's a simple problem. We've seen this before, sort of. Here's a bunch of acetate esters. Which of these are going to be the most reactive? Now, when I say most reactive, we're talking about the tetrahedral intermediate and the best leaving group. The best leaving group is the most stable anion or the strongest acid. The most stable anion is going to be the one where the phenol portion has electron withdrawing groups. And the king of all of that is going to be a nitro group. Yeah. The most stable anion, the strongest acid, the best leaving group. Down here we have methoxy, pumps electrons in, weakest acid, worst leaving group. So once again, just look at these mentally, trying to figure out who's who would be next. This is clearly the strongest acid. Here we have cyano, which is going to be pretty good. Chloro. This is electron withdrawing. Probably not as good as these guys. That's just benzene. This is the strongest, the most electron donating. Our order would be something like this. In physical organic chemistry, there's a correlation called sigma rho, where each of these are ranked by some number that reflects their relative reactivity, and it's just put on a sigma rho scale. Rho is the slope, sigma is the number assigned to the reactivity. Any questions? All right, let's do a little bit of quick review here. How do you make an acid halide? Well, we talked about reactions of carboxylic acids, and here are some. We can take a carboxylic acid and thionyl chloride. Remember thionyl chloride, remember all the way back to 234, the old days. Alcohols react with thionyl chloride, lose the OH, stick the chlorine on. Same thing here, we're going to lose the OH, stick the chlorine on, and make the acid chloride, benzoyl chloride. This is oxalyl chloride, nasty compound, very toxic. This is actually an example of a chlorine transfer reaction where the carboxylate will add, the chlorine will slip over, the OH will go with the oxalyl group, but the result is the same. We wind up transferring the chlorine to the carbonyl carbon. In this case, we make Yeah, this is something. This is 2-phenyl ethanoyl chloride. And finally, remember PBr3. We did PBr3 with alcohols and converted that into an alkyl bromide. Same sort of thing here. The anion will attack the bromine. We'll get an SN2 reaction. We will add to our carbonyl carbon and wind up with the acid bromide. Any questions? Again, this chemistry repeats itself. Back in 234, you talked about how to make acid bromides. We did that with PBr3. Here we're simply taking the OH group, substituting for PBr3, and we get the acid bromide. All right, acid halides. Once you have it, what can you do with it? Well, remember, this is a very reactive carbonyl carbon. And what's it going to do is going to add things to this carbon. If we just dump this in water, we would make a carboxylic acid. Alcohol, we would go straight to an ester. If we have an amine of some sort, we would go to the amide. The lab that we're going to do next week on Tuesday, we're going to take benzoyl chloride, so a benzene right here, react it with ammonia, and we will make benzamide. Lithium aluminum hydride, we're going to donate not 1 but 2 hydrides to this thing and make a primary alcohol. And of course, Grignards, we can add twice to make a tertiary alcohol, just like we did with esters. All of these reactions are the same. Now, I've set these next slides up to convince you that these are all the same. You don't have to remember anything except the basic addition-elimination mechanism. With our to make a carboxylic acid, let's take and add hydroxide to the carbonyl. When we do that, we get this tetrahedral intermediate. Now, which is the strongest acid? What's our best leaving group? This would be HX, like HCl, and that would be water. So this is -5 and that's 14. Well, this is going to win. And when it does, you simply make the carboxylic acid. Tetrahedral intermediate is the key. Understanding that and the notion of the pKa and the leaving group, and you got it. Instead of OH, if we did OR, what would we get? Same thing. OR is going to attack. Tetrahedral intermediate. pKa of -5, pKa of 16. This guy wins. And we get an ester. Nitrogen attacks. This is a little more complicated because our addition intermediate is this with-ion. Now, the nitrogen here is actually a better leaving group than the halogen. It is. Better leaving group. So this intermediate can have a lifetime on the order of 10 to the -8 seconds before nitrogen falls off and it goes back. In order for this to go on to product, you have to lose a proton here. Now we have pKa of -5. If this left, it would have a pKa of about 26. Big difference, right? There's a concept in physical organic chemistry called general acid-base catalysis. This is essentially how enzymes catalyze reactions. In an enzyme, you would catalyze this addition-elimination by having a group situated on the protein to readily accept that hydrogen. Once you get here, it's simple. We lose X and we make our amide. Making amides is very important in biochemistry because that's how you make proteins. Yeah.
Have we ever seen like NH3 or something to that effect, and then it has a halogen on the same molecule, I guess? Will it always lose that hydrogen and become an HX at the end?
Would this ever lose and form HX? Yeah. I mean, we lost the hydrogen. Here's it. So yeah, it makes HCl, HBl, or whatever.
But does that always happen when it's always like something H3?
Yep.
Okay.
Yep. This is an interesting reaction commercially. If we take, this is 1, 2, 3, 4, 5, 6, 1,6-hexane diamine, and this is 1, 2, 3, 4, 5, 6 bis-hexanenyl chloride. These can react first there, another one can react there, and this goes on and on and on, and you make a polymer called nylon 6. Why is nylon 6 such a strong thing? Because the amides, remember these amides are all conjugated and they're planar. They can line up with other amides in adjacent chains, form these hydrogen bonds, and it's a very strong sheet. This is why nylon is so strong. And this is how you make it. Lithiol, we've done lithiol before with things with leaving groups. Again, the hydride is going to add, form our tetrahedral intermediate. Obviously, the hydride cannot leave, so X must leave. In this case, we make an aldehyde. And by George, this is going to react with more lithiol, and we will make our primary alcohol. Simple addition of 2 moles of hydride to the carbonyl. That's going to be the same reaction as long as you have a decent leaving group. And finally, Grignards. Same sort of thing. We're going to add 1, make our tetrahedral intermediate. X is going to leave. We make a ketone, going to add another Grignard to give us our tertiary alcohol. The chemistry is all the same. There is one really cute reaction reminiscent of what we did with nitriles and diisobutyl aluminum hydride. If you take an acid halide and react it with this stuff, so we have tert-butyl groups all around, we can only donate 1 hydride. When we do that, we get this intermediate, but this is the anion stuck up here. So nothing else happens. It's just too big, too ugly, blocks everything from happening. When you dump it in water, this collapses, X leaves, and by George, you make the aldehyde. Single reduction, One more. We can also react acid halides with dialkyl copper lithiums. Same reaction we've seen before. Our group is going to attack. There's our intermediate. Our group is transferred over, and by George, we make the ketone. Nice way to go from an acid halide to a ketone. Dialkyl copper lithiums are useful because you can put darn near anything in as the alkyl group. Oh, I guess I lied. There is one more. If we react this with an acid, again, the same sort of thing. Now our tetrahedral intermediate, we have acetate as a leaving group. pKa about 5-ish, a little less. And here we have -5 for our halogen. Halogen will always leave, and we get the anhydride. All right, let's do a quick synthesis here. We're talking about acid halides, so let's use an acid halide in our synthesis. We're making a carboxylate ester. Now, how do we know to make carboxylate esters? Well, for the last 2 weeks, we've done Fischer esterification. So yeah, you could do that. We could take the carboxylic acid, benzoic acid, 2-propanol, and make an ester. But this is the chapter on acid halides, isn't it? So let's do it with an acid halide. Here we would need benzoyl halide and 2-propanol. Go ahead and write the two reactants. In the reactants down here, this carbonyl should have been bound to a halogen, and this was a simple alcohol. So we could do that with this pair, benzoyl chloride and 2-propanol. All right, how do we make benzoyl chloride? Well, we know we could make that from the corresponding carboxylic acid, right? How would we do that? Well, thionyl chloride usually works. Go ahead and write the reactants here to make benzoyl chloride. All we would need is benzoic acid, thionyl chloride, and that should work. And now finally, we look at our starting material. It's bromobenzene. We've added one more carbon. Now, how are we going to do that? We're trying to make a carboxylic acid from an alkyl bromide. You can make the nitrile and hydrolyze it, but can't do that with an aryl halide, can you? Remember one of my favorite reactions? You simply make the Grignard, and then you add little chips of dry ice to it. Carbon dioxide, very reactive molecule. It's like a ketene, very reactive molecule. So if we simply took this, converted it to a Grignard reagent, added CO2, we would have benzoic acid. Take bromobenzene and ether, add magnesium, stir it up a little bit. Once it looks good and happy, start adding little chips of dry ice, and by gosh, you made benzoic acid. Any questions? Well, we said that acid halides were the most reactive. The next most reactive acyl group is going to be the anhydride. But again, the chemistry is going to be exactly the same. Water is going to split it to make acids. Alcohol will split it to make esters. Amides will add to make, amines will add to make amides. And with-oyl will add twice to make primary alcohols. Exactly the same chemistry, just a different leaving group from the tetrahedral intermediate. See why this chapter is so easy once you get the concept of the tetrahedral intermediate. Let's look at the first one. All we're going to do is add hydroxide to a carbonyl and form this intermediate. Now we have two leaving groups. Acetate, pKa of about 5-ish. Water, pKa of 15.74 on a molar basis. Obviously, by 10 to the 10th, acetate's going to leave. And we get acetic acid as our product. Instead of adding hydroxide, if we had added alkoxide, what would happen? Exactly the same thing. Alkoxide will add. Our leaving groups are about 5 and 16. Acetate will leave, and we've just made an ester. If we add an amine, we have the same problem we did with acid halides. It's going to add but form the zwitterion. Now we have to deprotonate the zwitterion to make it neutral. So now we have leaving group of pKa 5-ish. This is like 26. Acetate's going to leave, and we make the amide. And finally, with-oyl is going to do the same thing it does with everything else. Going to add once. Acetate is going to leave, making an aldehyde, which is going to react again, giving us a primary alcohol. Exactly the same chemistry. Let's just go ahead and do a couple random reactions just to wake us up. After the last 2 weeks, you should certainly recognize Fischer's esterification. Carboxylic acid, alcohol, acid catalyst. We're going to lose 1 mole of water. Simply replace the OH with the OR. Another way we can make esters, going way back into 234. The carboxylate anion can be a nucleophile in an SN2 reaction. Now this actually works best if you have an activated halide here. So benzyl works, allyl works, maybe methyl. If you get too complicated, it doesn't work. But those guys work nicely. Again, the anion will simply attack and will make the corresponding ester. And finally, the reaction that works really, really well, but is just dangerous as heck to do, diazomethane reacts with carboxylic acids. We're going to protonate this to make this a methyl group. Carboxylate will attack SN2 style and will make the methyl ester. Beautiful reaction, quantitative yield, dangerous as all get out to be. All right, once we get esters, what do we do with them? Let's do our standard set here. In the presence of base, hydroxide will add, and we'll go back to the acid. In the presence of an amine, the nitrogen will add, we'll lose this guy, and we'll make an amide. With-oyl is going to add twice to give us the primary alcohol. And a Grignard will add twice to give us the tertiary alcohol. The mechanisms of all of these are identical. Simplest chapter we've got. Simply going to add hydroxide, form a tetrahedral intermediate. Now we have a little bit of a challenge, actually, because this has a pKa of 16, this has a pKa of about 16. So it's a real toss-up as to whether it goes forward or back. But you can dump in excess here, excess base, and push the equilibrium this way, so that alkoxide leaves, and you simply make the carboxylic acid. So this is a real toss-up. Again, both of these are essentially equal leaving groups. To make an amide, the nitrogen has to attack. Once again, we make our zwitterion. Again, this is a better leaving group than OR, much better. And in order to go to products, you have to remove one of these hydrogens. This carbonylamine, it's called, is now set up for elimination. Electrons come in, OR leaves, and we make the amide. Now, when we talked about this originally, I said this was a very important process in biochemistry. It is. We've all heard of transfer RNA, haven't we? This is how you make proteins, right? You have a chunk of DNA, and you have a ribosome, and you have all of these tRNAs that have matching codons on the bottom. And they have this little arm up top with the adenosine residue. And the adenosine residue is hooked to a specific amino acid. And it's hooked there through an ester linkage. So here's our adenosine, here's our tRNA, all the rest of it. This is the part that does the chemistry. So you have this growing peptide chain that's bound to the ribosome. And all the world you do is addition elimination. Nitrogen attacks. The enzyme is set up so that there are groups here to remove this proton at just the right time. So the leaving group here is going to be the sugar, and we wind up with a growing protein chain. Very simple carbonyl acyl transfer chemistry. Any questions? With-oyl, same thing we've seen before. We've actually done this reaction a couple times. With-oyl will add twice. Our only leaving group here is going to be alkoxide, making the aldehyde, which reacts with the second mole, and we get the primary alcohol. Exactly the same chemistry with a Grignard. Grignard anion will attack. Only possible leaving group here is the alkoxide to give the ketone, which reacts with a second to give the tertiary alcohol. Any questions? Well, we just made an amide from an ester. Let's just talk a little bit more about it. The unique thing about an amide is that we have this lone pair of electrons here on the nitrogen that's adjacent to the carbonyl. This can undergo resonance to form this zwitterionic species. Here we have a negative oxygen and a positive nitrogen. Now remember, in resonance, it's never either this or this. It's always somewhere in between. What we're really talking about is something like this, where we have partial bonding, partial positive, partial negative, but in order for this resonance to occur, these guys must be planar. So the oxygen, the nitrogen, and this hydrogen must be in the plane of the board here. This is the thing that gives proteins their unique shape. That the amide linkages all have to be planar. This is how you can have hydrogen bonding to form alpha helix, beta sheets, and whatever. This is with some orbitals. Again, here's our carbonyl orbitals. Here's our nitrogen. The resonance forms. We're simply going from a double bond here, double bond here. But again, in between, we simply have a continuum of electrons. If we rotate this bond, we lose the resonance energy. That's why amides are so good, or so useful, in making proteins. Any questions? Well, let's talk about amides a little bit. Amides are really, really unreactive when it comes to addition chemistry. And why is that? Well, that's because this really isn't a carbonyl. It's kind of like half a carbonyl, right? Because of the resonance. If you want to break it up, you want to do acid catalysis. That means you have to protonate the carbonyl with a strong acid. When you do that, now this is really electrophilic. Water can add and give us this intermediate. If we lose a hydrogen, I guess we don't lose a hydrogen, the nitrogen can leave as ammonia, and we've made a carboxylic acid. Why is this important? Because every time you eat a chunk of protein, what happens in your stomach? What happens? You protonate the amide linkages in your protein, you add water, eliminate the amino acid on the other side, and you have cleaved your protein. Now there are enzymes there that help because they help with all this proton transfer stuff. But the chemistry is really simple. Strong acid, protonate to carbonyl, this with-iron intermediate, and you can break the bond. Amides, you can also do the with-oyl thing. Once again, you add one. In this case, we're going to lose the aluminum thing and make the imine. This is a carbonyl equivalent, so we add another mole of hydrogen, and we go to the amine. So amides go all the way to the amines. One other magic reaction of amides that we should know, and it's really a cute reaction. Here we have a carbon with a double bond bonded to a nitrogen. Look at the elements here. We have H2O, right? That sounds familiar. We can eliminate H2O from an amide using thionyl chloride. And when we do, by George, we convert it to a nitrile. So a very nice way. We can take an amide, go to the nitrile, and then do other stuff with it. Any questions? All right, let me show you some exam questions from years gone by on this very subject, and let's see how we do. Here we have a tetrahedral intermediate. And if you notice, I gave you pKa's. What will be our products? Look around your tetrahedral intermediate. Split the little thingies off and say, what is the conjugate acid and what is its pKa? If we split off the methyl group, that would be methyl anhydride, a pKa of about 45. Whoa, no, not going to happen. Here is chloride. Chloride has a pKa of -5. This half would be phenol, pKa of 94. Now, which one is going to leave? The strongest acid. The strongest acid is going to leave. That's going to be our chlorine. And we're going to wind up with an acetate as a phenyl ester. Any question? Let's do it again. What are the products for the decomposition of this tetrahedral intermediate? Well, we can ignore the methyl group. We have chloride, pKa of -5. and methoxide, pKa of 16. Which is the strongest acid? Lowest pKa, strongest acid, -5 is going to leave, and we will form methyl ethanoate. This is so much fun. Let's do it again. Our leading groups here would be methoxide and acetate. So the conjugate acids would be methanol, 16, acetic acid, 4.76. Which is the strongest acid? Well, acetic acid, of course. So acetic acid is going to leave. This will be a carbonyl. This will be methyl benzoate. And now pretend that your entire grade on 235 depended upon your answer to this question. Our two leaving groups, methoxide and phenoxide. So pKa of methanol is what? 16. pKa of phenol is 9.4. Which is the strongest acid? Phenol. Phenol will fall off, and we'll be left with 2 carbon, that's an ethanoate, as a methyl ester. Methyl acetate. Let's just do a couple simple reactions, because you know I love reactions on exams. Our first reaction is simply, whose esterification? Fischer. Back in the old days, people developed much more of an appreciation of Emil Fischer, because chapter 5 or whatever in McMurry, in most textbooks, used to cover carbohydrate chemistry, and you do Fischer projections, and somebody would tell you how brilliant Mr. Fischer was to deduce the stereochemistry of all these carbons. But now they've moved that to chapter 29, and so you don't do that anymore. But Fischer was darn good. You know, the chemistry that they did back in those days, it was just amazing. And he made esters. Fischer esterification, you simply take a carboxylic acid and an alcohol, acid catalyst, and you make, in this case, ethyl benzoate. Here our nucleophile is going to be phenol. It's going to add to a carbonyl carbon, form a tetrahedral intermediate. Now, the pKa of phenol is about 9-ish. pKa of acetate is about 5-ish. This is going to be our strongest acid, so it's going to leave, and we will get phenyl acetate. Remember, when you add things to an ester, or really anything that we've talked about today with the decent leaving group, when you add a Grignard or lithiol to it, you're going to add 2 of them to the carbonyl, and you're going to lose all this interesting stuff on the side. It's all gone. So all we're going to do here is add 2 phenyl groups to our carbonyl carbon, and we're going to lose our phenoxide. We will wind up with this tertiary alcohol. 2 phenyl groups, and we lose phenoxide. Any question? Well, let's do 3 more. We have an ester reacting with an amine. Gee, that's just like making a protein, isn't it? What's our product going to be? It's going to be an amide. The nitrogen will add, form a tetrahedral intermediate. We have to lose a proton. And then our best leaving group is going to be the ethoxide anion. Once ethoxide leaves, nitrogen is bonded to the carbonyl, but remember we have a methyl group on the nitrogen. And the product would be N-methyl acetamide, or ethamide. Now, dialkyl copper lithium, in this case a diaryl copper lithium, reacts with an acid halide, but it's different than a Grignard or lithiol. In this case, our copper is going to form a bridge, and we're only going to move one of the alkyl groups, and we're going to be left with a ketone. So this is the only real exception you need to remember. Grignard and lithiol are going to add twice. Dialkyl copper lithium adds once. Now I gave away the last one. I said that lithium, a little bit of hydride, will add twice to an acyl group. So we're going to add 2 moles right here at the carbonyl. And when we do, we're going to go from benzamide, which we will make next week, to benzylamine. Yes.
There would be 2 hydrogens on that middle carbon, right?
Right. 2 hydrogens right there.
You could drop.
You could. It would look stupid, but you could. And let's finish up with 2 more. Acid anhydride with lithiol, carboxylic acid with thionyl chloride. Quickly jot down the products. The reaction with lithiol, just like everything else. We're going to add 1 mole of hydride here. Acetate's going to leave, isn't it? That's going to give us an aldehyde. Aldehyde will react with the 2nd mole of hydride to give the primary alcohol. And yes, you could draw on both hydrogens. And finally, if this was a simple alcohol and you had thionyl chloride, you would simply convert it to the alkyl chloride. Here we have an acyl group of carboxylic acid. We are simply going to convert this into the acid chloride. In our lab next week, we will take an acid chloride, benzoyl chloride, react it with ammonia, and make benzamide. Any question? All right, I think we're done.